In this lesson, we're going to look at composition of functions, which is a new operation that we'll be looking at for functions. And with composition comes inverse functions. Many tasks that we do in life are performed in sequence, just like putting our socks on and then putting our shoes on. We wouldn't put our socks over our shoes. We would put our socks on and then our shoes. There's an example here that talks about converting tons to ounces by using the conversion of pounds in between. This is the idea with compositions of functions. We'll use two functions put together in a particular way to get a result. Let's demonstrate with an example. So here we have two functions. F of x is 3x minus 7, and g of x is x squared plus 5. We want to use these two functions to create a new function, depending on how we're putting them together. So let's take a look at this notation. This circle here in the middle, this is our operator for composition. Now before, we've talked about operations on functions like f plus g, f minus g, f times g, and f divided by g. Those are our algebraic operations on functions that we've talked about way back in our chapter on functions, when we first talked about functions. Now we're adding another operation that we can do. Remember, with each one of these, we were really just putting the functions together with that operation between them. With composition, things work a little differently. Composition is defined to be the inner function inside the outer function. So f composed with g would be f of g of x. So what I mean by that is that this function, g of x, replaces x in the f function. Let's try it out. So f of g of x, but I know g of x is x squared plus 5. I'm going to replace the g of x with this x squared plus 5. And at this point you can see how this composition is very different from our algebraic operations. And now that I have x squared plus 5 in, function notation says whatever's inside the parentheses will replace the x in my function. So f of x is 3x minus 7, according to what's up top, 3x minus 7. But instead of x, we put in x squared plus 5. And then we work to simplify this expression out. Now we have something that we can work with. We can distribute the 3x squared plus 3 times 5 is 15, minus 7, and 15 minus 7 will give me 8. And so f composed with g of x would be 3x squared plus 8. We can also read this notation as f circle g or f of g of x. That reading is equivalent. For the moment, I'm going to skip number 2 and go down to number 3, mostly because I want you to see the difference when we switch the order around. So here we have g circle f. If I write it in the equivalent notation, by definition, g of f of x, now I'm going to put my f function in. So f was 3x minus 7, and g was x squared plus 5, but instead of writing x, I'm going to write whatever's inside that parentheses. This is just one step beyond what we were doing in the functions chapter, chapter 16, when we were putting in different things into the function instead of just x. We were throwing other things in there like x plus 5 or 2x minus 4 or what have you. We were putting in different things in there and then simplifying the expression. This is just one extra step in the front that we're adding on for notation. And so we have this expression here, 3x minus 7 squared plus 5. To simplify it, we need to multiply this out. And for a square here, we do not get to distribute that square inside the parentheses. because of that subtraction symbol. Subtraction and exponents do not play nicely together. So we multiply out 3x minus 7 and 3x minus 7. I like using the box. So 3x times 3x is 9x squared. 3x times negative 7 is negative 21x. And negative 7 is 49. So 9x squared minus 42x plus 49 plus 5. That plus 5 on the end. And we can simplify that to 9x squared minus 42x plus 54. We're not going to factor anything out. When we're simplifying these functions, we're just going to leave them as their written expressions here. It doesn't say get the expression and then factor it. We're not worried about factoring right now. We're just going to leave that as is. One last thing to notice about number 3, 9x squared minus 42x plus 54. If we scroll back up to number 1, that is not anything like the answer that we got in number 1. This operation, composition, is not commutative. It's not like addition and multiplication, where if we switch the order, we get the same answer. Composition is more like subtraction and division. If we switch the order, wildly different things happen. And that's exactly the case here. If we switch the order in which the functions appear, we'll end up with a different function. Let's look now at number 2. This one's a little bit different. Number 2 gives us a value for x instead of just having us use x. When we're given a value, we can look at this in 2 different ways. The first way that we can consider given a value is we can first find g of 2. So we find the value of g at 2, and then we plug that value into f. So let's do it this way first. G of 2, g is x squared plus 5, but x is now 2, plugging that 2 in for x. 2 squared is 4, 4 plus 5 will give me 9. So now I'm going to take the 9 and plug it in for g of 2. So g of 2 is 9. Because they are equal, I'm going to replace it. And f was 3x minus 7, but now I'm going to put that 9 in there, multiply it out. 3 times 9 is 27, minus 7 will give us 20. The second way that we can solve this very same problem is by using the very function that we created up here. Notice in number 1, we also have f of g of x. Number 2, we have f of g of 2. So number 2 is just telling us to take 2 and replace x with 2. So that's exactly what I'm going to do down here in my composition. 3x squared plus 8, f of g of 2. I'm going to put x here first. 3x squared plus 8. But now f of g of 2 means I'm going to have 3x squared plus 8 and put the 2 in for x and simplify. Exponents first. 2 squared is 4. Multiply. 3 times 4 is 12. 12 plus 8 is 20. And it should be the case that we do something in 2 different ways. They're both mathematically correct, and we get the same answer. We can also look at a composition of a function with itself. So f of x, and we'll take the function f, 3x minus 7, and put it inside itself where x was. So I'm going to use a different color for the outside f. We'll make it green. 3x minus 7, but I'm going to put 3x minus 7 in where the x was. And now I can simplify. 3 times 3 is 9. 3 times 7 is 21. Minus 7. And we get 9x minus 28.